In the next two videos, we're going to talk about how to solve exponential and log equations. In this video, I'm going to talk about a very special type of exponential equation, and that's one with a common base. And we'll talk about how to solve those algebraically, as well as how to check our answer with the graphing calculator. So, an exponential equation, remember, means that we have a constant base and our variable is in the exponent. And I got a very simple equation here. 2 to the something equals 8, which just by thinking about it, you'll realize that the answer is 3. And the way you realize that is that you recognize or you think of 8 as written as 2 to the third. In other words, what we've done is we've written both sides of this equation with a common base. And so if the bases are the same, obviously that must make the exponents the same. Therefore, x is equal to 3. And what I've just shown you is really the basis for solving exponential equations with a common base. What you do is you write your exponential equation with a common base, and then you make the exponents equal to one another. Now, just in terms of a graphical way to think about this, because we will want to move into solving more complex equations algebraically and graphically, but just in terms of graphically, I can think of this particular equation, if I think of this as two functions, y equals 2 to the x and y equals 8, then remember that something we've talked about in the past is that if I graph both sides of the equation as individual functions, so function 1 would be a graph looking like so, an exponential growth graph. Function 2 would be the line y equals 8. Then my solution is the x-coordinate of the point of intersection, which in this case would be the 3. Another way to think about solving graphically is to take your equation and set it to 0. So I'm going to set that as 2x minus 8 equals 0. And then graph the corresponding function, y equals 2 to the x minus 8, which I would know is a exponential growth graph shifted 8 units down, and so my graph would look something like this. And in this case, we would look for where y is equal to 0, which we know is the x-intercept, and so the x-intercept would represent the solution. So we have an algebraic way to get the solution if we have a common base, and we also have two alternate graphing solutions that we can use to get the solution. Alright, let's apply all this to a more complex situation. Alright, so here's our more complex exponential equation. We have constant bases and exponents involving variables, and we want to find out what value of x makes both sides of this the same. So first of all, let's look at solving this algebraically. And the way we're focusing on at the moment is by writing each side of the equation with a common base. Well, if I think about my bases 1/8 and 16, hopefully you'll realize that both of those can be written as 2 to the something. So for example, with 16, I know that 16 is 2 to the 4th. Put my exponent on the outside. And with 1/8, that can be written as 2 to the negative 3. Negative reciprocates, 2 to the third is 8. And by rules of exponents, I have an exponent to an exponent. We know that that's the multiplying rule for exponents. So we can write this. We can multiply the exponents to make that 2 to the negative 9 plus 6x equals 2 to the 36 minus 40x. And we've arrived similarly at what we had with our basic example. We have both sides written with a common base of 2. And if both sides are supposed to be equal, that logically means that this exponent has to equal that exponent. So we simply write negative 9 plus 6x equals 36 minus 40x. We have a nice simple equation that we can solve. 46x equals 45, and so x is 45/46, which as a decimal is 0.98 rounded off. But of course exact values are better. They're exact, so we're going to leave our answer as 45/46. So that's solving algebraically by writing both sides of the equation with a common base, in this case a base of 2. All right, let's check our work by solving this graphically. So we'll bring back our original equation. And when we solve graphically, as we said before, we have two options. We can enter both sides of the equation as their own function, so y1 and y2. I'm going to take advantage of my graphing calculator for this question. So here we go, 1/8 to the exponent 3 minus 2x. And our second equation, 16 to the exponent 9 minus 10x. And we can see our two graphs there, and what we're going to want is the point where they intersect, which is somewhere in this neighborhood. So I'm just going to zoom in on that. Number 2, zoom in. I'm going to put my center point somewhere around the point of intersection. Maybe I can see this a little bit more clearly. It's right in there somewhere. Let's just zoom in one more time. All right. Now when we solve graphically, what is generally expected is that you'll draw me a sketch of what you're seeing on your calculator, and down below here you'll tell me what your window dimensions are. So my window dimensions here are set from 0.65 to 1.9. So my x values are 0.65 to 1.9, and my y window dimensions are from negative 0.265 to the positive of that. I will indicate what my two functions are, y2 and y1. And then I know what I need to get is the point of intersection. So the point of intersection I can get my calculator to do that by using the intersection button. So there's my graph. I'm going to go second function trace, which is calculate, number 5 intersection, and the first curve is y1, the second curve is y2. My guess means move my cursor close to the point of intersection, and I get 0.978, so about 0.98, comma 0.114. Now remember, to solve the equation, our original equation only had x's in it, it didn't have y's. We introduced the y's in order to get a graph. So our solution is simply the x-coordinate of the point of intersection. And so we can say that solution is the x-coordinate of the point of intersection. Therefore, x is 0.98. Approximately, that's the disadvantage of the calculator, is that you won't get an exact value. You get a decimal approximation in this case. And remember, there is a second way you can solve graphically by making this into one graph instead of two, and that's simply by setting the expression to 0. And then what we're going to do is we're going to graph this equaling y. So on my calculator, I'm going to get rid of the second graph, and I'm going to go up to the top. Minus 16 to the exponent 9 minus 10x, and I'm going to graph the one graph. We've got a different graph this time, but we have a different function. I'm going to draw what I see on the calculator. I'm going to indicate my window dimensions. This time it's basic negative 10 to 10 on x and y. I've indicated what my function is. And now what I'm looking for, where my answer is showing up on the graph, is when y is 0. So that's the x-intercept. The solution to the equation is the x-intercept of the graph, or the 0 of the function. So therefore x equals, back to my calculator, second function calculate, get the 0 of the function, move my cursor to the left of the solution, right there, there, enter, to the right of the solution, there, close to the solution. So when y is 0, x is 0.98. Okay, so that shows you the two ways to solve graphically. It shows you how to present your work in terms of showing the graph, the window dimensions, stating in words how your graph gives you the solution, and then finally stating the solution.